Hello, future engineers, subscribers, viewers, and students. Here is a video in differential equations 2, and this is part 2. And I'm going to discuss principles and sample problems, especially on the applications of the first order differential equations, such as population growth and decay, uh, exponential growth, applications of applications in engineering economy, about continuous compounding, but I do not give an example here. You just wait until engineering economy. Then we have family of curves, flow problems, velocity of escape, and even problems in dynamics. Mechanics, for example, where the acceleration is varying with time. So that's it for this video. So first, let's have the solutions to higher order differential equations. And the roots, there are so many cases. When the roots are real and distinct, the type of solution would be in the form y equals c sub 1 e to the r sub 1 x plus c sub 2 r sub e to the r sub 2 x plus dot 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 plus c sub n e to the r sub n x. So it all depends on the number of distinct real roots. So that's the form of the solution. Case 2, the roots are real and repeated. So let us say the roots are repeated twice and they are real. So therefore, the solution would be y equals quantity c sub 1 plus c sub 2x closed e to the r1x plus quantity c sub 3 plus c sub 4x closed e sub r sub 2x, and so on and so forth, depending on the number of repeated real roots. Then case 3, we have roots that are complex conjugates. Example of the roots would be a plus b plus minus bi. And so the form of solution would be quantity c sub 1 cosine of bx plus c sub 2 sine of bx closed times e to the ax. So for the real part uh, of the root, then we have e to the ax, just like in cases 1 and 2. Then when the case 4, when the roots are pure imaginary numbers, so for example, plus minus bi, then the solution would be free of this part e to the ax. So it will just be c sub 1 cosine of bx plus c sub 2 sine of bx. And lastly, when the roots are repeated and the roots are pure imaginary numbers, example plus minus bi, and they are repeated twice, then the solution would be in the form quantity c sub 1 plus c sub 2 x close cosine bx plus quantity c sub 3 plus c sub 4x close times sine bx. Although the best approach here is to find the solution to differential equation in the backdoor way, but there are situations where the checking is long, very long, especially. So you just familiar with the types of solutions, then the direct way of solving solution or finding the solutions to differential equations would be easier when you master all this. So let's have uh, the following exercises. As I said, there are situations where the checking process is longer. So there's no need to check that anymore. It's long. So, however, when you apply this method, checking, you should be very good in obtaining the differentials of the function or the derivative of the function. So let's have this 6 2 for 7 exercises. Determine the solution of the following equations. So we have third derivative of y with respect to x minus 6 times second derivative of y with respect to x plus 5 times first derivative of y with respect to x equals 0 and so on. So for the solution, the answers, by the way, are given, provided. The answers may not be written in the form presented here. The constants may interchange position as long as the general form of solution would be the same. So for number 5, for example, y, let's transform that to root cube minus 6r squared plus 5r equals 0. Then you can factor out r, and the second factor would be quadratic equation. And since your calculator is also allowed to solve or find the roots of third degree equation, even fourth degree equations, then after that you get the root of the following are the roots. Root 1 is 0, R2 is 1, and root 3 is 5. You can check that easily. So therefore, the solution would be y equals c sub 1 e to the 0x, which is just c sub 1, plus c sub 2 e to the root 2, which is 1x, so e to the c sub 2 e to the 1x, then plus c sub 3 e to the root 3, which is 5x. Simplifying, so y equals c sub 1 plus c sub 2 times e to the x plus c sub 3 times e to the 5x. So that's the solution. And only in this problem where I'm going to present the checking. So that means y prime, the derivative of this solution is c sub 2 e to the x plus c sub 3 e to the 5x times 5. So that would be c sub 2 e to the x plus 5 c sub 3 e to the 5x. So that's y prime, or the first derivative. Then the second derivative is y double prime equals c sub 2 e to the x plus 5 c sub 3 e to the 5x times 5. So that would be y prime equals c sub 2 e to the x plus 25 c sub 3 e to the 5x. Then the third derivative is y triple prime c sub 2 e to the x plus 25 c sub 3 e to the 5x times 5, or that is c sub 2 e to the x plus 125 c sub 3 e to the 5x. So that's the third derivative. We then substitute these values into the original differential equation. So we have third derivative of y with respect to x is c sub 2 e to the x plus 125 c sub 3 e to the 5x minus 6 times second derivative quantity c sub 2 e to the x plus 25 c sub 3 e to the 5x, then plus 5 times dy dx, or 5 times y prime. So 5 times quantity c sub 2 e to the x plus 5 c sub 3 e to the 5x. So if we check this, it must be 0. So we have c sub 2 e to the x minus 6c sub 2 e to the x. So that's negative 5 c sub 2 e to the x, and there is also 5 c sub 2 e to the x. So that means the term with e to the x is eliminated. Then for this 125 c sub 3 e to the 5x minus 6 times 25 c sub 3 e to the 5x, so that's negative 25 c sub 3 e to the 5x, and there is also 5 times 5, 25 c sub 3 e to the 5x. So it is indeed 0. Therefore, the answer is correct. So we proceed to example 6, sample 6. So we then change that to sample 6 to 4r square minus 3r minus 10 equals 0, where r is the root required. So this is quadratic, expect two roots. The roots are root 1, 2, root 2, negative 5/4. So therefore, the solution, because these are unique real roots, so solution should be y equals c sub 1 e to the 2x plus c sub 2 e to the negative 5/4 x. So that's the solution to example 6. Example 7, let's transform that to 4r cubed minus 4r squared plus r equals 0. Factor out r, and it becomes r times quantity 4r squared minus 4r plus 1 equals 0. And this is a perfect square trinomial, so r quantity 2r minus 1 squared equals 0. So one root, real root is 0. The other roots are repeated twice. r2 equals r3 equals 1/2. And since the other root is repeated, then for r1, y equals c sub 1 plus we have c sub 2 plus c sub 3x e to the 1/2 x, or e to the x over 2. So the solution y equals c sub 1 plus quantity c sub 2 plus c sub 3x e to the x over 2. Number 8, let's transform that into r squared minus 4r plus 5 equals 0. And using the quadratic formula or your calculator, the roots are 2 plus minus I, which are complex conjugates. So y equals c1 cosine x plus c sub 2 sine of x e to the 2x. So we have, for imaginary roots, we have c sub 1 cosine 1x, because that's 1i, plus c sub 2 sine 1x, then close, then for the real part, e to the 2x. So that's the solution to 7. Number 8, that is r squared minus 4, number 9 rather, r cubed plus 9 times r equals 0. If we factor out r, then that's r times quantity r squared plus 9 equals 0. So r2 is, r1 is 0, r sub 2 is negative 3i, r sub 3 is positive 3i. So the solution would be y equals c sub 1 for this root r1, and for the second root, which are pure imaginary roots, they are represented by the term c sub 2 cosine 3x and plus c sub 3 sine of 3x. So those are this is the answer. Okay. Number 10, r cubed plus 3r squared plus 9r minus 13 equals 0. So using your calculator there, we expect 3 roots, and the roots are real root 1, r1 is 1, r sub 2 negative 2 plus 3i, r sub 3 negative 2 minus 3i. So the type of solution will be y equals c sub 1 e to the 1x, or e to the x. Then plus, for the complex conjugate roots, quantity c sub 2 cosine 3x, because that's 3 plus minus 3i. So y equals c sub 1 e to the 1x, or e to the x. Y equals c sub 1 e to the x, plus quantity c sub 2x, c sub 2 times cosine of 3x plus c sub 3 sine of 3x close times e to the negative 2x. So y equals c sub 1 e to the x plus quantity c sub 2 cosine 3x plus c sub 3 sine of 3x close e to the negative 2x. So that's the solution. Then lastly, number 11, we rewrite this as r to the fourth plus 18r squared plus 81 equals 0, which is a perfect square trinomial represented by quantity r squared plus 9 quantity square equals 0. So r therefore is square root of negative 9, so that's plus minus 3i, pure imaginary roots which are repeated twice. So therefore, the expected equation would be y equals quantity c sub 1 plus c sub 2x cosine of 3x plus quantity c sub 3 plus c sub 4x sine of 3x. Oh, that's the expected answer. Then for one application on family of curves, sample 12, find the differential equation of a family of parabolas having their vertices at the origin and their foci on the x-axis. So the parabola is both open to the right and open to the left with vertex at the origin. So the expected equation or the equation of the parabola is y squared. The constant is the length of latus rectum. Since it is open to the right or open to the left, the expected equation is y squared equals plus minus latus rectum times x. So y minus 0 quantity square equals plus minus latus rectum times x minus 0. So it is reduced to y squared plus minus lr times x. The arbitrary constant is plus minus lr. So if we solve for plus minus lr, then it is equal to y squared over x. And by obtaining the differentials, this is fraction. So differential of this arbitrary constant is 0. So 0 equals open quantity denominator times derivative of numerator 2y dy minus numerator y square differential of the denominator differential x all over denominator square x square. So 0 times x square is still 0. And for these two terms, y is common, so we also divide by y. Then the first term becomes 2x dy. The second term is minus y dx. So the answer, differential equation of family of parabolas with center at the origin and focus on the x-axis would be 2x dy minus y dx equals 0. Sample 13, find the differential equations of family of circles with center on the x-axis with given radius. So we have two arbitrary constants here. The x coordinate of the center, which is denoted by h, and the second constant or variable of integration here is the radius of the circle. The expected equation of the circle with center on the x-axis, so y is 0, x or h is unknown, and then the radius is given. The expected equation, standard equation, is quantity h minus h, x minus h quantity square plus y square equals r square. So that's the expected equation. Quantity x minus h square plus y square equals r square. So from here, if we obtain the derivative of the equation with respect to the first uh, variable, which is x, is we can eliminate r square. So 2 times quantity x minus h raised to 1, so that is still 2 times quantity x minus h, then plus so 2 times quantity x minus h plus 2 times y prime equals 0. So 2 is common. We can divide everything by 2 and simplify that to x minus h plus y prime equals 0. We then eliminate h. We can eliminate h from this form. Or we may write h in terms of the other variables. So h is x plus y prime. So we can eliminate this second arbitrary constant by differentiation. So derivative of h with respect to x is 0. So 0 equals 1. Derivative of x is 1 plus derivative of product y double prime plus y prime times y prime equals 0. So 1 plus y double prime plus y prime equals 0. Simplifying that equation, we have y double prime plus quantity y prime square plus 1 equals 0. So that's the differential equation of this family of circles with center on the x-axis and with given radius. So finally, find the velocity of escape in Earth. So the velocity of escape, we don't need to derive it anymore. It's just familiar, square root of 2g h RH. So square root of 2g sub h r sub h. That's the formula for the velocity of escape. And g sub h is the pull of gravity of the near the Earth's surface, which is 9.81 meters per second square, or converted to kilometers per second square, that's 0.00981 kilometer per second square. While the radius of the Earth from spherical trigonometry or from your surveying is 6,371 kilometers. So square root of 2 times 0.00981 kilometer per second square times 6,371 kilometers. So using your calculator, the velocity of escape is 11.18 kilometers per second. So I hope you can imagine that. That's how fast the speed of the, let us say, space rocket, 11.18 kilometers in just 1 second in order to escape from the Earth, or else it cannot escape, it will go back.